John has been was a colleague of mine for many years, and I'll say a little bit more about him. But first, I should say a few words about Robert Hofstadter, and in whose memory this lecture series happened, because a more extensive introduction will be given by Peter Michelson at the public lecture to which you're all invited tomorrow evening. So, Hofstadter was a physicist who was worked at Stanford and of course famous for many things, both instrumentally and in theory, and in particular he won the Nobel Prize, I believe, in 1960 for his examination of nucleons using the electrons, a then very novel technique at the time, and he shares, I think, with Rudolf Mossbauer. He influenced many other aspects in physics, and also in his later years in astrophysics, and Peter Michelson will tell you more about his role in the Compton Gamma Ray Observatory, the ING mission instrument at EGRET on that, which I think he passed away the year before it was launched, and that vision carried forward to Fermi Gamma Ray Telescope, which is still operating. So it's a great pleasure for me to acknowledge the memory of John Hofstadter, Robert Hofstadter, and let me now say a few words about our distinguished speaker, Professor John Preskill. As I said, he's the Richard Feynman Professor of Theoretical Physics at Caltech, and he was an undergraduate at Princeton and a graduate student at Harvard, where he worked with Steven Weinberg, I think was his advisor, and others, and was in those days working in theoretical particle physics. Since then, he then, I think, was at Harvard in the Society of Fellows and as a physics professor, and then he moved to Caltech in 1983, joining the faculty, which is when I first met him, and he has always had a very strong interest in the foundations of quantum mechanics, both as expressed through particle physics, but also as in a more modern way, as expressed through quantum information, quantum computing, quantum, and the interface between quantum mechanics and the classical world, which I think is going to be a large part of his talk today. There are many things I could tell you about John, but one of them I recall a lunchtime conversation with John. I think it must have been about 2000, and I asked him, well, when are we going to have a quantum computer that I can use on my desk? And he said, you will hear three answers to this question. The first one is in 5 years' time, because that's a funding cycle. The second one is never. And the third one is, I already have one. So I'm interested to hear, amongst many other things, his current view of that problem, but in particular he's going to tell us about learning in a quantum world. So let's give a welcome to John Preskill.
Well, hold on. Well, I have no reason to doubt Roger's veracity, but I don't have any recollection of that conversation. It's always great to be at Stanford, one of the great centers for physics research in the world, and a special honor to be giving this lecture in honor of Robert Hofstadter, who I'm a great admirer of his scientific achievements. And as Roger has reminded us, I started my career doing theoretical physics with a focus on elementary particle physics and early universe cosmology, but I made a shift in the 1990s toward quantum information science. And the way I view this field of quantum information is that we're still in the early stages of the exploration of a new frontier of the physical sciences, what we could call the frontier of complexity, or the entanglement frontier, different from the frontiers of particle physics or cosmology, but like those, very fundamental and exciting. We're acquiring and perfecting the tools to create and precisely control very complex states of matter, very highly entangled states, which are so complex that we can simulate them with the most powerful conventional computers that we have, or predict how they'll behave very well with known theoretical tools, and that opens opportunities for discovery. I want to talk about how tools from machine learning and artificial intelligence can help us to probe the quantum world, but first I'll give an overview of quantum computing, its current status and prospects. Our conviction that this entanglement frontier will be fruitful to explore rests largely on two important ideas: quantum complexity, our basis for thinking that large-scale quantum computers would be able to solve problems that are too hard to solve with conventional computers, and quantum error correction, our basis for thinking we really can scale up quantum systems to the degree where they can solve those very hard problems. And both of those ideas build on the underlying concept of quantum entanglement. That's the word we use for the characteristic correlations among parts of a quantum system, which you can think of this way. Imagine a book which is 100 pages long, and if it's a conventional book written in bits, every time you read one of the 100 pages, you learn 1% of the information content of the book. And after you've read all the pages one at a time, then you know everything that's in the book. But suppose instead that it's a highly entangled quantum book written in qubits, the quantum analog of bits, with the pages highly entangled with one another. Then when I look at a single page, I just see random gibberish, which reveals almost nothing to distinguish one highly entangled book from another. And even after we've read all of the pages one by one, we know essentially nothing about the information content of the book. And the reason is that in the quantum book, the information isn't recorded on individual pages. It's stored almost entirely in the correlations among the pages. And if you want to read the book, you need to make a collective observation on many pages at once. That's the essence of quantum entanglement, and it's very different from notions of correlation that we're accustomed to. And what's quite remarkable is that these highly entangled states speak a very extravagant language, which is different from the language that we understand or that our conventional computers understand. A very extravagant language such that if you wanted to translate a complete description of all the correlations among just a few hundred qubits into ordinary language, that would require more numbers than the number of atoms in the visible universe. So it'll never be possible to construct such a description. Now that in itself doesn't mean that by manipulating the qubits we can perform useful tasks. But we have a couple of reasons for thinking that quantum computing will be powerful. One is that we know of some problems which are believed to be too hard to solve with conventional computers, for which theoretically a quantum computer could solve the problem efficiently. Finding the prime factors of large composite integers is the best known example of that. But really, most tellingly, we just don't know how to simulate what a quantum computer does with a classical computer, which opens the possibility it can perform tasks that ordinary computers would never be able to emulate. Now, we don't expect that quantum computers have unlimited power. We don't think, for example, that they'll be able to find the exact solutions to the hardest instances of hard combinatorial optimization problems. So they have some advantage, but not unlimited advantage over conventional computers. It's still quite remarkable that there seems to be interesting classification of problems. There exist problems which are classically hard, too hard to solve with conventional computers, but quantumly easy, can be efficiently solved with quantum computers. So we have a very strong incentive to understand better what are these problems that are classically hard and quantumly easy. Factoring is an example. We'd like to know more. We've learned a lot about this in the last 20 or 30 years, but we still have a great deal more to learn about where quantum advantage lies, and I think our understanding of that will accelerate when we have large-scale quantum computers that we can experiment with. But if you're a physicist, there's a natural place to look for such problems, because we expect that with quantum computers, we should be able to simulate efficiently any process that can occur in nature. We don't think that's true of conventional computers, which can't efficiently simulate very highly entangled matter. So with quantum computers, we should be able to go further in probing properties of complex molecules and novel materials, and also explore fundamental physics in new ways, for example, by simulating high-energy collisions of elementary particles, or the quantum behavior of a black hole, or what was happening in the very early universe right after the Big Bang. It's not a new idea that a quantum computer would be able to address problems like these. It was proposed by Richard Feynman over 40 years ago. And we're just now getting to the point where our quantum technology is sufficiently advanced to begin to do interesting things. So evidently, building a quantum computer is hard. And what makes it hard is that we want a quantum platform to simultaneously satisfy a set of criteria which are nearly incompatible with one another. We want our qubits to interact strongly with one another so we could rapidly process the information that they encode. We don't want the qubits to interact with the environment, which would cause a quantum computation to fail. But we do want to be able to control the qubits from outside, make them do what we want them to do, and eventually read them out to find the answer to a computational problem. And it's quite difficult to build a platform that simultaneously satisfies these desiderata. So it's only after some decades of technical progress that we've gotten as far as we have. So why is it so important that qubits not interact with the environment? It's because of a fundamental difference between quantum information and classical information. Namely, you can't observe a qubit without disturbing it in some uncontrollable way. And so that means even if we don't observe the qubit ourselves, if information about the state of the qubit leaks to the outside world, where in principle it could be observed, that's just as bad. So if we want a quantum computer to work reliably, we need to keep the information that it processes nearly perfectly isolated from the outside world during a computation, and that's very hard to do because our hardware is never going to be perfect. But we've understood in principle how it can be done, appealing to the idea we call quantum error correction. And the essence of the idea is that if we want to protect quantum information from damage, we should encode it in a very highly entangled state, encode it very non-locally, so that when the environment interacts with parts of the quantum system locally, none of the information that's encoded is revealed to the environment, and so it doesn't need to be irreversibly damaged. And we've understood how to process information that's encoded in that very highly entangled form. So where do things stand now? There are a number of different approaches to instantiating qubits, which have been steadily advancing. A lot of different physical realizations of a qubit are possible. We could, for example, encode a qubit in a single photon, which is in either one of two optical modes, or a single electron, which has a magnetic field which can point either up or down, or a single atom, which could be either in its lowest energy ground state or some long-lived excited state. Those are all remarkable encodings because the information is carried by a very simple single quantum system, but thanks to technical advances in recent decades, we've learned how to control those systems fairly well. Or we could encode a qubit in a more complicated system, like a superconducting circuit that which conducts electricity without resistance at very low temperature. And that's very remarkable too, because then the qubit is encoded in the collective motion of billions of pairs of electrons, and yet we can make it behave as though it were a single atom. It's useful to have a word for the current era of quantum information processing. The word NISQ has caught on. It's an acronym. It stands for Noisy Intermediate Scale Quantum. Intermediate scale reminds us that we have systems of width of order 100 qubits, which is a sufficiently large number so that we can't, by brute force, simulate with a conventional computer what a 100 qubit quantum computer does. But noisy reminds us that these systems are not error corrected, and the noise is a serious limitation on their computational power, on how long a computation I can perform and still read out a useful result. Now for physicists, NISQ is exciting. It gives us opportunities to explore the behavior of very highly entangled matter in regimes we haven't had access to experimentally before. And it might have practical applications that have economic value in the relatively near term, but we're not really sure about that. We shouldn't think of NISQ as something that's going to change the world by itself right away. Rather, it's a step towards more powerful quantum technologies we're hoping to develop in the future. So I think a fair assessment of where things stand now in the NISQ era is that NISQ is valuable for scientific exploration, but there isn't any proposed application of NISQ computing which has commercial value, for which quantum advantage has been demonstrated when we make a fair comparison to the best classical hardware running the best algorithms for solving those same problems. And we don't have persuasive theoretical arguments that I know of indicating that commercially viable applications will be found that don't make use of quantum error correction and fault-tolerant quantum computing to make the computing system much more reliable. If we look ahead, we can envision, if we had a perfect quantum computer, which wasn't noisy, we can envision applications to, say, chemistry and materials using just a few hundred very high quality qubits, and then we'd be able to run simulations of quantum systems which are beyond the reach of what classical computers can do now or in the near future. But the catch is we don't have perfect quantum computers. The current state of the art is that every time you perform an entangling operation on a pair of qubits, the probability of an error is a little bit below 1%. We can foresee that improving to about 0.1% in the next few years. But we would like to run applications that are sufficiently large that the probability of error per gate should be 1 in a billion or less, which is far beyond the current state of the art. Quantum error correction can get us there, but at a cost, because quantum error correction has a high cost in overhead, in the number of qubits and number of gates that we have to perform. So to run these applications, it might mean that we have to have thousands of physical qubits for every very well-protected logical qubit that we use in the computation, and that could bring the qubit count up into the millions, which is a big step from where the technology is likely to be in the next few years with hundreds or thousands of qubits.
John, are those numbers on the bottom physical qubits or logical qubits?
The numbers on the bottom are physical qubits. On the previous slide, they were logical qubits. Now, meanwhile, it's really important to try to come up with hardware instantiations which have much lower physical error rates. And there are a number of approaches to doing that which have been suggested and which are being explored experimentally. And these are a few that I'm partial to, which I'm not going to explain in detail, but they all have in common that some part of the protection against error is built into the design of the hardware itself, rather than being completely achieved by the software at a higher layer of the stack. And these are all in early stages, and we don't know how well they're going to pan out. But it's really important to try these alternative approaches, because if we could achieve substantially better gate error rates, that would extend the reach of quantum computing in the NISQ era before error correction, and it would significantly lower the overhead costs for the error-corrected quantum computers that we're envisioning building in the future. So really, there are two main open questions confronting quantum computing today. How are we going to scale them up? to quantum computing systems that can really solve hard problems. And once we do so, what will be the most important applications for science and industry? And I consider both questions to be wide open. We have a lot of basic research and engineering to do before we have conclusive answers. At the same time, it is an exciting time for the field, and I think we'll see a lot of exciting developments over the next couple of years. We'll continue to see encouraging progress toward realizing quantum error correction in actual devices, and that progress will probably accelerate. We can expect to see scientific discoveries that are enabled by programmable quantum simulators and circuit-based quantum computers that can explore the dynamics of many entangled particles. And there's also a merger going on of quantum matter and quantum metrology. If we can get many qubits to be created in some suitable, very highly entangled state, that can have advantages in the precision of measurements, and for example, it could enable us to build much better clocks. Okay, now I want to shift gears and talk about how tools for machine learning can help us deepen our understanding of the quantum world. When we're trying to understand quantum phenomena, we face this dilemma. We live in a quantum world, but we're classical beings. And sometimes our classical nature might impede our ability to interact with, learn from, and understand the underlying quantum reality. I want to talk about two ways in which we might enhance our understanding of the quantum world, which I'll call learning with classical machines and learning with quantum machines. When I say learning with classical machines, what I have in mind is that it's possible for a complex many-qubit state to translate that state to a succinct classical description of the state. In doing so, we discard a vast amount of information, but we might still be able to retain a lot of physically relevant information, and then using classical machine learning tools, generalize from the data we obtain in quantum experiments to predict the behavior of quantum systems in situations that we haven't encountered in the lab up until now. And we might use classical machine learning to recognize when some qualitatively new phase of matter has been created in the lab that we've never seen before. But with quantum machines, we can in some cases go further. We can imagine capturing quantum data, transducing it to a quantum memory, and then processing it with a quantum computer. And for some properties of quantum systems, that enables us to learn the properties with an exponential advantage over conventional experiments. That is, the number of experiments that we need to learn the property with high accuracy can be exponentially fewer if we make use of quantum processing. And that can enable us to unlock features of nature that would otherwise be too deeply concealed. When we're trying to understand large, complex quantum systems, we confront a curse of dimensionality. For a system with n qubits, the Hilbert space has a dimension which is exponential in n. And in principle, it's possible to write down a complete classical description of an n-qubit system when n is large. But it's not at all practical to do so because that description is exponentially large. And the number of experiments that we would need to do to learn the description is exponential in n. And if we wanted to use that description to predict properties of the system, we would have to do an amount of classical processing, which is also exponential in the system size. But we can take the point of view that we don't really need a complete description. We might be satisfied with a much more succinct description if it enables us to predict and understand many physically relevant properties of the system. So we've been developing for a few years an idea we call classical shadows of quantum states, especially with my wonderful collaborators, Robert Huang and Richard Kuhn. And the idea of classical shadows is that if we have access to a complex many-qubit state, we can, by doing experiments that are feasible now, translate that quantum system into a succinct classical description, and then make use of that to predict very many properties of the quantum state, and furthermore, have a rigorous guarantee that our predictions are accurate with high probability. Now, examples of properties we can predict with classical shadows are expectation values of local observables, few-point correlation functions, expectation values of local Hamiltonians, entanglement entropies of subsystems, the fidelity of a quantum state with some target state, and many others. So how does it work? Well, we imagine that we have access to many identically prepared copies of an n-qubit quantum system that might be prepared by a quantum computer or by some protocol that we carry out in the lab. So let's say a total of capital N of those copies are at our disposal. Now, our measurement protocol is going to be defined by some ensemble of unitary transformations that we can apply to the n-qubit system. And if we want this protocol to be practical, then we want each one of those unitary transformations to be ones that we can actually perform in the laboratory. And we also want them to be transformations we can write down succinctly in classical language. And then what we do for each copy of the quantum state that we access is we randomly select one of the unitaries from the ensemble, and then we measure in the standard basis. So we generate an n-bit string. And that produces one snapshot of the state, which is the inverse of the unitary we applied, acting on that computational basis state we obtained in the measurement. So there are two sources of randomness in this scheme. There's the randomness of the unitary that we apply before the measurement, and there's the randomness of the quantum measurement process itself. And if we average over both the choice of the unitary and the measurement outcomes, this defines a map acting on the unknown input state that we're measuring, some completely positive trace-preserving map. So as an example, suppose it's a single qubit, and our unitaries consist of either the identity or a 90-degree rotation about the x-axis or the y-axis. Then the measurements, when we average over the choice of measurement and the measurement outcomes, define a depolarizing map in which the input state is preserved with probability 1/3, and it's replaced by a completely mixed state with probability 2/3. Now, if the measurements we performed are tomographically complete, that means that this map is an invertible map. Its inverse isn't a physical process we can actually perform in the lab, but it doesn't need to be. We will apply it not to quantum data in the lab, but to classical data that we've stored in a classical memory, the outcome of our measurements, the snapshots we've obtained. So for each snapshot, we can apply the inverse of the map to that snapshot. I'll call that an inverted snapshot. And now if we average over the choice of unitary and the measurement outcome, that provides an unbiased estimator for the unknown state. It converges to the unknown state. So if I want to predict in that unknown input state the expectation value of some observable, what I can do is for each one of the inverted snapshots, compute the trace of the inverted snapshot times the observable, and then average over all the inverted snapshots, and that's guaranteed to converge to the expectation of the observable. But then how many copies do we need to get a good estimate? To say something about that, we need to be able to bound the variance of our estimator, and we also need to be able to make some statement about how large deviations from mean values are extremely rare. And we can say something about both those things. And the result is the fundamental theorem about classical shadows. So let's suppose there's some set of capital M observables that we're trying to learn. We can get an upper bound on the variance of the estimator I described for each observable. That depends on the protocol, on that ensemble of unitaries that define the protocol. We call that the shadow norm. So suppose we denote the shadow norm by B. The number of copies we need in order to predict all of the observables in this list of M increases only logarithmically with the number of observables on the list if B is a fixed number. So the reason we can predict a number of properties which is exponentially larger than the number of copies that we measure is because large deviations from the mean are exponentially rare. Now, as I said, this shadow norm, which determines the variance and therefore how many copies we need to make a good estimate, depends on the protocol. So let me give two examples. One we call random Clifford measurement. What that means is that before we make the measurement, we apply a random unitary in the set of Clifford transformations. Those are ones that map polyobservables to polyobservables, where a polyobservable is a tensor product of poly matrices. Or if you like, they're the transformations that are generated by 90-degree rotations of the Bloch sphere and control knot gates acting on pairs of qubits. So we can do a random Clifford measurement and then measure and find our inverted snapshots to get estimates of the observables. In this case, the shadow norm is essentially the Hilbert-Schmidt norm. It's the trace of the square of the observable. So an example of an observable which has a small Hilbert-Schmidt norm is a low-rank observable. For example, the overlap with some specified pure state. So what we're saying here is that we can, by collecting these snapshots, predict the fidelity, the overlap with a number of target states, which is exponential in the number of copies that we measure. The trouble with the random Clifford measurement is random Clifford transformations require fairly deep computations. I have to have a number of steps in the computation, which is roughly the same as the number of qubits. And if I have, say, a few hundred qubits, that's too hard to do with the technology we have now. But we can consider something easier, which we call random poly measurement. And what that means is that for each one of the qubits, we decide uniformly at random to measure in the x, y, or z basis on the Bloch sphere. And in that case, the shadow norm is proportional to the operator norm, the maximum eigenvalue of the observable, but it's also exponential in the weight of the observable, the number of qubits on which it acts non-trivially. But if I consider any local observable, which acts on some constant number of qubits, then we have some reasonable value for the variance of the estimator. So I could consider, for example, a local Hamiltonian, which is a sum of such local observables with a number of terms, which might be a polynomial in the total number of qubits, and the number of copies that I need to make a good estimate of the expectation value of the Hamiltonian, the energy of the state, increases only logarithmically with the system size, with the number of qubits. Now, just to make sure it's clear, here I'm reiterating the statement of the classical shadow theorem in the case where we do random poly measurement. So we have some unknown state, and we can have access to multiple identically prepared copies. For each one of the qubits, we just decide uniformly at random to measure the poly observable, x, y, or z. That determines all of our snapshots. We can find the inverted snapshots, and then we can use those to estimate M-independent local observables, which have constant weight, with a number of copies, which is only logarithmic in the number of observables we're trying to estimate. So I told you about two specific examples of classical shadow protocols. One we could call local, because we just scramble each qubit individually by measuring it in a random basis, and that gives us access to local observables. And the other we could call global, because the Clifford circuit globally scrambles up the state before we measure it, and that gives us access to some global observables characterizing the state. But the disadvantage is that we need to do a circuit which has relatively high depth. Or we can consider something in between, where we apply a circuit of intermediate depth, or we let the system evolve under chaotic dynamics for some intermediate time and then measure. And as we consider a longer and longer evolution time, the protocol gives us access to higher and higher weight observables, but the computation we need to do to find the inverted snapshots becomes harder and harder. You could ask about what happens when the protocol is noisy, when our measurements are imperfect. But a nice feature of the fact that we measure in random bases is that simplifies the structure of the noise, which makes it easier to characterize the noise. And once it's characterized, we can include the noise in our inversion to determine the inverted snapshots in order to get an unbiased estimator even in the presence of noise. But the catch is that then the sampling error in characterizing the noise is going to be a contributor to the variance of the estimator, and that means as the measurements get noisier, we'll need more and more measurements in order to make good estimates. So in a recent review, we distilled the philosophy of this randomized measurement approach to an aphorism: measure first, ask questions later. We don't need to know what properties we're going to want to predict at the time that we make the measurements. That can be decided later. And in fact, many of the applications of classical shadows that have been carried out in the last couple of years have been done by reanalyzing data that was originally taken with a different purpose in mind. So here's an example to illustrate the advantage of classical shadows coming from our original paper. It's based on an experiment done a few years ago by the Innsbruck group with 20 qubits in an ion trap, and they were trying to characterize the low energy states of a model of one-dimensional quantum electrodynamics. And this is Hamiltonian for the 20 qubits, which has a number of terms which scales like the number of qubits squared. They used a variational method to search for low energy states, repeatedly measured the energy. But they measured not just the energy, but also the variance of the energy, the variance of the Hamiltonian, because that variance should be zero when you find an energy eigenstate, and they could use that to validate that energy eigenstates had actually been found. If you want to measure the square of the Hamiltonian, that's of order n to the fourth terms, which is a lot of terms that we have to measure when n is 20. And in their original analysis, they came up with a customized protocol for measuring all of those observables, which required a number of copies of the state, which grew linearly with the number of qubits. But with classical shadows, we only need a logarithmic number, which is a big advantage when the system is large. And if we know exactly what observables we need to learn, we can make it even more efficient. So now that we've seen that it's possible to translate a quantum system into a succinct classical description while retaining the ability to predict many properties, one wonders whether we can learn about quantum systems and predict properties of quantum systems with classical computers using classical shadows as an input. Understandably, there's been a lot of interest the last couple of years in applying machine learning to solving quantum problems. And most of that work has been heuristic and empirical. But we were interested in whether there are settings in which we can prove that such methods give us accurate predictions. And we were able to find a few settings in which that's true. One is predicting properties of ground states of local Hamiltonians. So let's suppose we have some family of Hamiltonians. They're smoothly parametrized by some real parameters. And we have the ability during a learning phase to sample ground states of Hamiltonians selected from this family. And then after the training is complete, we are to predict properties of ground states of other Hamiltonians in the family that are different than the ones we encountered during training. So our idea is that whenever we encounter a ground state, we immediately do a feasible measurement to obtain its classical shadow. And then after collecting sufficiently many classical shadows as training data, we then try to generalize to obtain a classical representation of other ground states that are in the same family. We were able to show that that can be done efficiently with an amount of training data and an amount of classical computation that just scales polynomially with the total size of the system. If the Hamiltonian is gapped, if there's a non-zero spacing between the energy of its ground state and the energy of its first excited state. So in this case, the learning is completely classical, but we make use of a quantum platform to prepare and measure, to acquire the classical shadows, of the ground states. And in fact, you can argue, subject to complexity theory assumptions, that if we have access to data and then do classical computation, we can solve problems and predict properties that would be too hard to solve if we didn't have access to the data. So the data is very empowering. Here's an example to illustrate the idea, based on an experiment done a few years ago by the Harvard group. With a chain of 53 Rydberg atoms, you can just think of those as qubits, where there's a term in the Hamiltonian which favors the qubits pointing in some preferred direction on the Bloch sphere. But there's another term in the Hamiltonian that penalizes two qubits that are close to one another and are both pointing in the same direction. So there's a competition between those two tendencies, which results in some non-trivial phase structure. So we see different phases with different types of order indicated in this diagram by the different colors. So what one can do is select at random a few points in the phase diagram, collect their classical shadows, and then try to generalize from that data to predict properties of ground states at other points in the phase diagram, like, for example, the star and the diamond and the cross. Now we can predict any local property we want, but just as an example, suppose we want to predict the expectation value of the Pauli operator Z for qubits at each position in the chain. And the pink line here shows the exact answer. The diamonds are the prediction of the classical ML from the training data, and they follow one another pretty well. If you try to just make predictions based on a few nearby points, the ones that are closest by in the phase diagram, then the prediction performance is not very good, which is what's shown here. So the machine learning really is leveraging the ability to sample a lot of points in the phase diagram. Actually, our rigorous theorem doesn't guarantee good prediction performance in this case. It tells us that we can predict accurately if we have training data and test data which are both in the same gapped phase of matter, which isn't the case here because we have these phase boundaries and we're collecting data from several different phases, but the predictions are still pretty accurate.
But you need data from all the phases to get good predictions?
Well, we don't need data from all the phases, but if we fix the amount of data in the phase where we're trying to predict, and then we add additional data from the other phases, that improves the predictions. So it's not useless to get the data from the other phases.
You can't predict, if you have data from two of the phases, properties in the third phase.
Well, I'm not sure that we can't. I mean, one way of thinking about it is that, you know, from the ground states, you're learning something about the Hamiltonian. And if you really knew the Hamiltonian, then you should be able to predict even in the other phases. Okay. Is that me? No. So another setting we considered is identifying quantum phases of matter. So now we consider a supervised training scenario where during training we're offered samples, say, from two different phases of matter, labeled phase A and phase B, and then after training is complete, we're offered unlabeled states and we're asked to which phase they belong. So our idea here is each time we have a quantum state, we convert it to its classical shadow, and then the problem becomes, can we classify the shadows according to the phase from which they were collected? And we show that that can be done efficiently under a physically motivated assumption. The assumption being that it's possible to identify the phase looking at a lump of bulk matter which has some constant size independent of the system size, which is reasonable for gap phases. We wouldn't expect to have to look at a chunk of matter much larger than the correlation length. So the learning strategy here is kind of a standard one. We map all the classical shadows to a very high-dimensional feature space, and then we try to learn a classifying function in the feature space. That function isn't known in advance. It's learned by the ML, and so that can provide some guidance to the physicists who are trying to understand how the two phases are distinct from one another. So here too we've done a lot of numerical experiments, and here's one illustration where the goal is to distinguish between a trivial and a topologically ordered phase in two-dimensional matter. So when we say there's a distinction between these phases, a computer science way of saying that is that if you start out with the trivial phase, which has only short-range correlations, and you want to create the topological phase, which has long-range quantum entanglement, then in order to do so with a geometrically local quantum computation, the length of the computation would have to grow with the system size. So what we did here is we considered representatives of these two distinct phases, a product state and Kitaev's toric code state, and then we applied low-depth random circuits to the states to make them harder to recognize. And then we collected classical shadows for the states, used our feature map, and then did a principal component analysis to see if the ML could distinguish between the two types of states. And so what's shown here is the result of applying a depth 3 circuit where the states are 100 qubits on a 10 by 10 lattice, a 10 by 10 square lattice. And you can see that the two phases are very easy to distinguish in that case. What's shown here is with just one principal component indicated, how the two phases can be distinguished from one another as we increase the depth of the circuit that we apply, the number of time steps in the circuit, to the two samples. And until we get up to a depth of 5, which is half the total linear size of the sample, the two phases are still well distinguished from one another. All right, now I want to talk about how in some cases, if we do quantum processing, we can do better than with just classical processing of data from quantum experiments. So I'd like to consider, as before, a situation where we have access to many identically prepared copies of a quantum state. And our goal, after measuring many copies, is to be able to predict some property of the state. But now I want to distinguish two different scenarios. In the first, which I'll call the conventional scenario, every time we receive a copy, we measure it. And we're allowed to do any measurement we want for individual copies, and they can even be adaptive, meaning the measurement I perform on the next copy could be conditioned on outcomes of measurements I performed in previous rounds. Contrast that with the quantum enhanced scenario. And what that means is we take multiple copies of the state, put them in a quantum memory, and then do a quantum computation across the copies and measure. and then use that data to predict the properties we're interested in. And what we can show is that for some tasks, exponentially fewer experiments suffice to make good predictions in the quantum enhanced setting compared to the conventional setting. And in fact, the measurements that we need to make in the quantum enhanced setting are simple enough so we can do a proof of principle experiment using 40 qubits on the Google Sycamore processor. So here's some data from one of those experiments. So the situation is we have a way of preparing multiple copies of the state. They're not difficult to prepare, so we can do it on the quantum computer. And in the quantum enhanced scenario, we have up to 40 qubits, so we can load up to 20 qubit states and have 2 copies. In the quantum enhanced scenario, we make entangled measurements across the copies, and these are not so difficult to do. I just do projection onto the entangled belt basis for a pair of qubits, one chosen from the first copy and one chosen from the second copy. And then after all the measurements are complete, we're offered 2 observables, which are high-weight observables, acting on many qubits. And we're challenged to say which one of the 2 has the higher expectation value. And we can show that in the conventional scenario, when you can only measure copies one at a time, the number of copies that you need to measure grows exponentially with the total size of the system with the number of qubits n. What's shown here in the lower left is plotted as a function of the system size. We could go up to 20 qubits because we had 2 copies of 20 qubits stored in our 40 qubit device. On the vertical axis, the number of experiments we did to make good predictions, which we defined as getting the right answer to which one had the larger expectation value 70% of the time. Ideally, if we had a perfect quantum computer, the number of copies that we would need to make good predictions would be a constant independent of the system size. Because the real device has some noise, the number of copies that we use does increase slowly with the system size. But by the time we get to the largest system size we considered, 20 qubits, we have a rigorous lower bound on the conventional scenario that says the number of experiments that would be needed to achieve that same prediction performance is larger by over 3 orders of magnitude. We can also consider predicting properties of processes rather than states. Well, this is another experiment that we did using Sycamore, where now we're trying to distinguish between 2 different symmetry classes of unitary transformations. They're random unitary circuits. In one case, they're general unitary circuits. In the other case, they're restricted to be real and orthogonal unitary transformations, which you can think of as being drawn from a time reversal symmetric class. And we can show that in the conventional scenario, when we can only measure 1 copy at a time, that a number of copies, which is exponential in the system size, is needed to distinguish between the 2 classes. But in the quantum enhanced scenario, we consider some fixed input. We apply the transformation to the same input twice. Then we do entangled measurements across the copies, like I described before. And then we can take that data and do a principal component analysis, and that's what's shown on the right. In the case of the quantum enhanced scenario on top and the conventional scenario below, both for circuits that have a 1-dimensional geometry and have a 2-dimensional geometry. And we can see that in the quantum enhanced scenario, the 2 symmetry classes are easily distinguished, and in the conventional scenario, we can't tell them apart at all. All right, so to sum up, broadly useful applications of quantum computing might still be a ways off. We expect that we'll need quantum error correction to run applications that are of practical interest, and that will require a much larger number of physical qubits, as best we can tell, than what we currently have. So how long it'll take to do that scaling up is still not clear. But already the existing platforms are exciting from the point of view of fundamental science. They're enabling us to study quantum dynamics in a regime we never had access to before in systems of hundreds of qubits in highly entangled states. Classical shadows of quantum states gives us an experimentally feasible way of translating a complex many-qubit state to a succinct classical description from which we can make many predictions. In fact, with a number of copies of the state scaling like log m, we can predict a number of properties, number of properties, which is exponentially larger than the number of copies that we measure. Furthermore, we don't need to know what properties we want to predict at the time the measurements are made. We can measure first and ask questions later. Access to data from quantum experiments can enable classical machine learning to make predictions in regimes where if we didn't have access to data, the quantum problems would be too hard to solve. And quantum enhanced experiments in which we make use of quantum memory and quantum processing can have an exponential advantage relative to conventional experiments. So as our ability to manipulate the quantum world advances, we can envision becoming increasingly adept at generalizing from the data we collect in experiments on quantum systems to predict properties of systems we haven't encountered in the laboratory before. And we can envision future quantum sensing networks which collect quantum data, transduce it to a quantum memory, and then process that data with quantum computers, which could have an exponential advantage over conventional sensing experiments. So these results were obtained by these brilliant collaborators who are listed here, who are really responsible for all of these beautiful theorems. And we all hope that our work will stimulate some fresh thinking about where to seek advantage with quantum technology. Thanks a lot for listening.
Thank you very much indeed, John, for a wonderful lecture. It reminded me of three things that I always admired. The first was your ability to remain focused on the foundations of the business and to see what is really important and essential. And I would say that this has just been recognized by the Canadians with the award of the J.S. Bell Prize, which congratulations.
Thank you.
The second is your ability to inspire your protégés. You've won many teaching awards at Caltech, but also students and postdocs who've gone on to illustrious careers in quantum computing and quantum information. And the third is your coining of phrases which take these deep concepts, and like quantum supremacy and so on, and they came up several times in this talk, and then are used, as in some sense, to carry the much deeper ideas forward. So thank you very much for this talk. We've got time for questions, so let me ask for questions from the audience. Okay, yes.
Oh, hi.
So this is related, it's related to Daniel's earlier question. So if I try to use these machine learning methods to understand phase diagrams, I wonder what do we expect in general as this capability of generalization? It means that if we want to predict the, like say, triangular lattice Hubbard model behaviors from square lattice, right? So is this kind of, like, is there some sense that we can understand like what kind of training data is sufficient for what kind of generalization?
Well, you know, there's what you can prove and there's what you can demonstrate empirically, and there's a gap between them. We've been mostly interested in what we could prove, and so we were able to prove that within a gap phase of matter, you could use training data to make good predictions efficiently. It was an observation which we hadn't expected in advance, that data in other phases for the same family of Hamiltonians could have provide some leverage in improving the predictions. I think where quantum computing is going to become increasingly important, most likely, is in providing training data for AI, because our advances in understanding chemistry and materials, I think, will be increasingly driven by artificial intelligence. But we need the training data, and we already have good methods for much of material science and chemistry, which are very successful, except in that corner of highly correlated systems that we don't understand very well. That's where quantum computing is useful. And we'll need a lot of training data in that highly correlated regime in order for AI to be able to make good predictions. And how well it'll work, I guess we'll see.
So at the start you talked about recursive dimensionality, that Hilbert space goes exponentially with the number of qubits. And then you talked about these classical shadows giving you an estimate of the density matrix. Of course, the density matrix is quite, square root of the number of dimensions, whatever. So do you actually have to store a density matrix of the system to use these classical shadows? Or is there a method that doesn't actually involve storing?
Well, I don't have to store the density matrix, but what we can say about the performance of classical shadows is, in the case where we just do single qubit random measurements, we can, with a reasonable number of samples, predict all of the marginal density operators of constant size. So you can pick any, 4 qubits in the system, and from the classical shadow you can get a good estimate of the marginal density operator when you trace out the other n-4 qubits. If you're trying to predict marginal density operators which have more and more qubits, of course it gets harder and harder. And that was the exponential that we saw in the variance of the estimator.
Thank you.
Because I wanted to come back to the quantum book analogy. And so I was sort of wondering, are there things which you're able to get from this classical shadowing, things that you could sort of get by reading 10 pages of the book, but not by reading 1,000 pages?
Yes, I think that's right. Well, it depends which version of classical shadows you mean. I think when we do what I call the random Clifford measurement, it does have access to some properties of the global entanglement that go beyond what you'd be able to see if you just looked at subsystems of constant size. But for the case where we just did random single qubit measurements with a reasonable number of samples, what we're able to learn are the marginal density operators of subsystems that are not so large.
So if I say I wanted to learn something...
So in other words, we could learn a page, but we couldn't learn many pages.
So if I want to make a superconducting phase, and then I'm making a state of that regime where there's a state of that which is a superposition of a Josephson junction with 0, 1, 1 flux point, whatever it is, on a loop. Is that something which intrinsically you can't get out from these kinds of measurements?
You mean, well, I don't know that you can't get that out. I guess whether that's really a global property in the sense that I'm talking about, I'm not sure that it is. Yeah.
More questions? Yes. Yeah, the back.
Oh.
I did have a question earlier. I thought that maybe there's now, but you alluded to this earlier. I'm curious. It's not trivial to prove theorems just about good old classical machine learning. In practice, it's often complicated by things like the non-conventional loss function or whatever else. So could you say a little bit more about what was special here that enabled you to prove theorems about even the classical part of learning?
Well, so the question was, there's a paucity of rigorous results about the performance of classical machine learning. So how was it that we were able to prove things in this particular setting? I don't think that, you know, the proof techniques that we use are really so novel, and it could be used for some classical problems. I think when applied to quantum problems, the results, in a sense, are more surprising. And I think the reason for that is that, I mean, understandably, we have the intuition that in a quantum system there are many properties we might be interested in, but they don't commute with one another, so they're not compatible. And so that, at least for me, and before we did this work, gave me the intuition, you know, that we would need many samples in order to learn many non-commuting observables. And so the thing, I mean, the basic theorem about classical shadows, it's just statistics, but I think the thing that came as a surprise is that the non-commutativity of the observables that we're learning doesn't create an obstacle.
Yeah, I was wondering, do you see any near-term opportunities for quantum information to enhance classical machine learning, so the other way around?
Oh, yeah. So this is, so I talked about quantum machine learning in a certain sense. I talked about using quantum processing to learn about quantum properties. But I think your question is, what are our expectations for how quantum processing can improve the tasks that we use classical machine learning for today? You know, will it be better at telling cats from dogs or driving autonomous vehicles? I don't see encouraging evidence that quantum machine learning will be better than classical machine learning for tasks like that. I'm a little more pessimistic about that than I might have been 5 or so years ago, because there were a number of interesting proposals for ways in which quantum machine learning could be used with an advantage over classical machine learning. And one after another, they became dequantized, meaning people found that people were challenged by these quantum approaches to find classical methods for solving the same problems with similar speed-ups, and generally succeeded. So the number of such examples of quantum advantage in machine learning when it doesn't involve solving a quantum problem has shrunk to almost zero. That doesn't mean that they're not out there, but I don't see a lot of evidence as of now that there will be big advantages for many of the tasks that we use classical machine learning for now.
I'm classifying this between a Schrodinger's cat and a Schrodinger's dog. That would be.
Yeah, that would be. It would be good at that.
Last question, I think, at the back. That's okay.
How optimistic are you that there will be the advances in quantum hardware needed to further this work?
I only heard part of that. How optimistic am I that there will be advances in quantum hardware?
Yep.
That what?
That will allow you to further this work to greater and greater lengths.
That will allow me to what?
Allow you to further this work.
Oh, further this work. Well, I'm sure there will be advances in quantum hardware. They're occurring steadily. Right now, the biggest limitations are twofold. There's a limit to how many qubits we have in the platforms that are, under good control. And most limiting is that the gate error rates are just too high. The gate error rates are improving. And, every once in a while, a different approach is proposed that turns out to have some advantages. Probably if I were talking 5 years ago, I wouldn't have considered neutral atoms held by optical tweezers as a competitive platform, but it's advanced enormously, over the past 5 years, and I think will continue to. But it's all really hard stuff. Getting much better error rates than 1/10%. Very challenging. I think, eventually we'll have that, but it might not be for a while.
Okay, I think we better finish at this time. I just wanted to say thank you very much, John, for a talk that has been...
Thank you.
Okay. complete the sentence, for his talk has been inspirational, current, and challenging. And for those of you who did not catch every nuance in John's presentation, come to the popular talk tomorrow, where you will be able to get caught up on this. Thank you again very much.